In the world we see every day, events feel reassuringly deterministic. If you throw a ball, you can calculate exactly where and when it will land, provided you know its speed, angle, and air resistance. The planets orbit the sun with such predictability that eclipses can be forecast centuries in advance. Classical mechanics, as laid out by Newton, gives us a clockwork universe where causes lead to definite effects. It is comforting to imagine that the world unfolds in a chain of certainty. But is this certainty fundamental, or just an illusion born of scale? At the quantum level, determinism dissolves into probability. An electron does not follow a single path, but spreads out like a wave of possibilities, collapsing into one outcome only when observed. Radioactive atoms decay at random moments we cannot say when, only with what probability it might happen. Quantum mechanics describes this with extraordinary precision, yet it insists on uncertainty at its core. Isn't it strange that the foundation of reality is not certainty but chance? The paradox deepens when we realize that macroscopic certainty somehow emerges from microscopic uncertainty. If every electron in a ball follows probabilistic rules, why does the ball itself obey deterministic equations of motion? The answer lies in statistics and scale. When trillions upon trillions of quantum particles interact, their uncertainties average out. The random fluctuations cancel, leaving behind stable, predictable behavior. This is why a gas of molecules obeys the smooth laws of thermodynamics, even though each molecule zips about unpredictably. Could it be that determinism is not fundamental, but an emergent property, like a straight road built from countless crooked bricks? A less well-known fact is that even in quantum theory, the evolution of the wave function is itself deterministic. Schrödinger's equation unfolds smoothly, without randomness. The probabilistic element arises only when we make a measurement, forcing the system into one definite outcome. This raises a haunting question. Is the uncertainty in the universe truly fundamental, or is it a reflection of our limited ability to observe and interact with it? The interpretations of quantum mechanics divide sharply on this point. Some argue the randomness is real, others say all outcomes exist simultaneously in many worlds, and what we see is just our branch of the story. So the paradox remains: the universe at its deepest level may be probabilistic, yet our lives feel deterministic. Out of fundamental uncertainty emerges the solidity of cause and effect, as though order crystallizes out of chance. The puzzle is whether determinism is a higher-level illusion or probability itself hides a deeper law we have not yet discovered. Which possibility is more unsettling? That certainty is only a convenient fiction, or that chance itself is the bedrock of reality? Classical mechanics, as developed by Newton, describes the world as a clockwork universe. Every object follows precise mathematical laws of motion, determined by its initial conditions. If we know the position and velocity of a ball, we can predict exactly where it will land. In this framework, uncertainty comes only from lack of knowledge, not from nature itself. Determinism implies that the future is fully encoded in the present. At macroscopic scales, this model works remarkably well. It provides the intuitive certainty we experience in daily life. Engineers calculate the trajectory of a spacecraft with near-perfect accuracy using classical mechanics. It is like a train on fixed tracks. Its future position is entirely determined by where it starts and how it moves. At quantum scales, determinism gives way to probability. Electrons, photons, and other particles do not have definite paths but exist in superpositions of possibilities. Measurement collapses these states into particular outcomes, but which outcome occurs cannot be predicted exactly. Quantum mechanics only gives probabilities for different results. This indeterminacy is not due to ignorance, but a fundamental feature of reality. Nature itself seems to operate with uncertainty built in. The quantum world defies classical predictability. A radioactive atom may decay at any moment, but only the probability of decay per unit time can be calculated. It is like rolling dice. Each roll is uncertain, even if the rules are fixed. Quantum mechanics encodes probabilities in the wave function, which evolves deterministically until measurement. The wave function spreads across multiple outcomes, each with a calculable likelihood. When observed, the system appears to choose one result randomly. This duality, deterministic evolution plus probabilistic outcome, creates the core paradox. The uncertainty principle deepens this, limiting how precisely we can know quantities like position and momentum. Reality, at this level, resists absolute prediction. Probability is woven into its fabric. The double-slit experiment shows electrons forming an interference pattern, but each individual hit is unpredictable. It is like a weather forecast. Laws predict overall patterns, but exact raindrop locations remain unknowable. Despite fundamental uncertainty, macroscopic objects behave predictably. A baseball contains trillions of quantum particles, yet its path follows classical laws. Randomness at the microscopic level averages out when enormous numbers of particles are involved. This statistical smoothing creates apparent determinism. The quantum noise is drowned out by the sheer scale of the system. Predictable order emerges from fundamental uncertainty. Determinism is thus an emergent phenomenon, not a fundamental one. A toss baseball follows Newton's equations, even though its atoms are governed by quantum rules. It is like listening to a symphony. The individual instruments may fluctuate, but together, the music follows a clear rhythm. Quantum decoherence explains how probabilistic states appear classical. When a quantum system interacts with its environment, superpositions rapidly collapse into definite outcomes. This process suppresses interference effects, leaving systems that look deterministic. Macroscopic objects are so entangled with their surroundings that their quantum fuzziness disappears. Decoherence bridges the gap between quantum uncertainty and classical certainty. It does not eliminate probability, but hides it beneath environmental interactions. Certainty thus emerges from entangled chaos. A dust particle in air decoheres almost instantly, behaving like a classical object rather than a quantum wave. It is like a drop of dye dispersing in water. The original sharp color disappears into the environment. Even in our macroscopic world, probability still shapes events. Weather patterns, stock markets, and biological processes include unpredictability. Much of this unpredictability stems from complexity, but some comes from underlying quantum uncertainty. Human experience blends determinism with chance, depending on the system observed. We perceive certainty where quantum fluctuations cancel out. But probability never disappears completely. Life is lived in the balance between predictable order and unpredictable noise. Random genetic mutations arise from quantum events, yet evolutionary trends follow deterministic natural selection. It is like shuffling a deck of cards. The outcome is uncertain, but the rules of the game guide overall patterns. The clash between determinism and probability raises profound questions about free will, causality, and the nature of reality. If the universe is fundamentally probabilistic, then the future is not fully determined by the present. Yet the predictability of classical systems suggests an underlying order. Philosophers debate whether probability reflects incomplete knowledge or true indeterminacy. Interpretations of quantum mechanics differ on this point, from many worlds to Copenhagen to hidden variable theories. The paradox highlights our incomplete understanding of what reality means. Einstein resisted quantum randomness, insisting God does not play dice with the universe. It is like a script that appears fully written, but still allows actors to improvise lines. Physicists seek frameworks that reconcile determinism and probability. Some interpretations claim all outcomes occur simultaneously in branching universes, preserving determinism globally. Others propose hidden variables that restore predictability beneath quantum mechanics. Still, others accept probability as fundamental, redefining determinism as emergent. Experiments continue to test these competing views. Yet no consensus exists on whether certainty or uncertainty lies deeper. The tension remains at the heart of modern physics. Bell's theorem showed that no local hidden variables can fully explain quantum correlations, challenging deterministic models. It is like trying to decide whether a coin toss is truly random or just too complex to calculate. The paradox is that certainty in the macroscopic world emerges directly from fundamental uncertainty in the microscopic world. Probability governs the building blocks, yet determinism describes the structures built from them. The two are not opposites, but complementary aspects of reality. Determinism is the large-scale face of a universe, whose foundation is probabilistic. Without uncertainty, no stability or adaptability would exist. Without determinism, no coherent structures would form. Together, they weave the strange duality of nature. A cat's heartbeat is predictable and regular, yet each atom in its body follows probabilistic rules. It is like a mosaic, tiny, irregular tiles forming a stable, orderly picture. So, John Julien,